This is a brief introduction to the kinds of data that scientists use to understand paleoclimates. There are really two kinds of data. The most common are proxy data sets. Now, proxy simply means that it is a measure of something that responds to climate. So tree rings grow wider in very good growing conditions and narrower in years where growing conditions are poor. So it's measuring something that responds to climate, but it isn't a direct measurement of climate. We can also get data from pollen, from fossil leaves, from historical records, and from measuring isotopes in things like ice cores, sediments, corals, and we'll talk about all of those. The only thing we can really directly measure from the past are trapped gases in ice cores, and ice will trap air from many thousands of years ago. We can look at the composition of that air in those gas bubbles. We also have instrumental records, measurements of temperature and water salinity and other rainfall and other kinds of things that go back to about 1880, depending on which record. So one at a time, tree rings. Living trees, of course, can be several hundred years old, and fossil trees contain records that are decades long. Sometimes a geologic event can be recorded in a tree band and provide a time marker. Volcanic eruptions and large earthquakes can disrupt tree growth, for example, and they allow scientists to correlate the bands with a particular year. Tree ring data goes back about 1,000 years. Another common fossil record of proxy data for climate change are pollens. Pollens, of course, are produced by plants growing in an area, and they're commonly collected in lake bottoms. And this is for an example of pollen data from a lake in Minnesota, where you can see that over time the kinds of things growing there have changed, and scientists can correlate that with general climate patterns over the past, in this case, 15,000 years. Climate data and lake records go back 800,000 years in various places. Now, stomata are a kind of breathing hole on the backside of the leaves, and they let in CO2. If the CO2 in the atmosphere is really high, you don't need as many, and if it's lower, you need more. So scientists have looked at fossil stomata, and here's an example of one, and counted their density on fossil leaves to get an indirect measurement of how much CO2 might have been in the atmosphere at that time that plant lived. This method has been used back 400 million years ago. People also look at historical data. For example, the price of wheat. If the wheat prices are particularly high, that means the crop was particularly bad that year. So you can get a sense of whether it was cold or wet, or the conditions were otherwise not good for growing wheat. Another kind of historical record are flood records. Egyptians have kept flood records on the Nile River for thousands of years. One measurement that scientists make that tell us something about climate going back in the past are isotopes. This is a graph of oxygen isotope versus time going back 900,000 years, and this is from an ice core. Does that shape look familiar? It should. It's very close to the shape of the Milankovitch insulation curve. The graph is marked warmer and cooler as we move in and out of glacial periods going back, in this case, 900,000 years. So you've probably seen something about fractionation before in your chemistry classes. Just as a brief review, remember that isotopes are elements of the same element that have different mass. Oxygen 18 is heavier than oxygen 16. H2 is heavier than H1. Evaporation is a physical process that will fractionate those two isotopes. It will pull the lighter one more readily than it pulls the heavier one, and that makes sense. It's got to lift it up, right? So it takes more oxygen 16 than the ocean has, and changes the ratio in the cloud, and that changes the ratio in the rain. And if you understand the physical process, then you can measure things like the oxygen isotope composition of something that formed in the ocean, like a coral, or something that formed on the land like ice, and understand what the temperature must have been in the past. So we're measuring the isotopes, we're calculating a temperature. In Greenland and Antarctica, we have ice core records that go back 800,000 years, and we can measure the oxygen isotopes, the hydrogen isotopes, and the air bubbles in this ice. We can also see things like volcanic eruptions, which show up as ash, or even droughts, which show up as dust in the ice core, and that gives us even more information about climate. Here are some temperature data from the Volstok ice core, and these are measured oxygen isotopes that are calculated then as temperatures. And you can see in this case time is moving from right to left, so 150,000 years ago up until today. On the left, the lower numbers, -8 degrees Celsius, those are temperatures variations from today. So the deeper down, the stronger the ice age, and the higher points on this graph are interglacial periods or warm periods. Another thing that we measure oxygen isotopes in are cave deposits called speleothems. Cave deposits form from dripping water. So the water from the rain comes through the ground into the cave, makes deposits that can be dated by year, and can calculate the oxygen isotopes of the cave deposits, which reflect the rainwater. So that's another way to use oxygen isotopes to measure climate. And speleothems go back for sometimes 600,000 years. Corals also are measured with isotopes to gather some information about paleoclimate. Corals can live a very long time. They have annual growth bands like trees do, and they can give you a snapshot of something like 400 years of history, either from today back 400 years, or a snapshot back in time several thousand years ago with several hundred years of history there. The coral records have shown El Nino cycles, for example, have happened for thousands and thousands of years. And another way we use oxygen isotopes going back in time is by looking at these little critters called Foraminifera. These are very small microscopic critters in the ocean called forams, and they float around in the near surface. They create their shells out of ocean water, and when they die, their shells fall to the bottom. We can go back 4 to 5 million years ago and look at forams as old as that and get a record of the ocean chemistry going back that far in time. By the way, you've seen forams before. Remember when we were looking at relative time and you put together a time sequence using forams and how they changed with time? They're also a very good time indicator on the ocean floor.